गुड इवनिंग एंड वेलकम टू द ब्लैक होल। हमारा आज का सेशन है प्राइम नंबर्स के बारे में। आप जानते होंगे कि अ प्राइम नंबर इज़ अ नंबर इज़ अ होल नंबर ग्रेटर दैन वन दैट हैज़ ओनली टू फैक्टर्स, दैट इज़ डिजिट वन एंड द नंबर इट्सेल्फ। बहुत सादा सी डेफिनेशन है, आप पीछे देख सकते हैं बोर्ड में ऑन टॉप राइट 2 3 5 7 11 13 17 19 एंड सो ऑन। मगर मैथमेटिशियंस के लिए प्राइम नंबर्स में बहुत फैसिनेशन है। क्यों है उसका एक अंदाज़ा आप मेरे बाईं साइड पे जो कोट लिखा हुआ है उससे अंदाज़ा लगा सकते हैं। समथिंग स्ट्रेंज इज़ गोइंग ऑन विद द प्राइम नंबर्स। वो स्ट्रेंजनेस क्या है, वो मिस्ट्री क्या है, उम्मीद है कि आज के सेशन में हमें उसका बेहतर अंदाज़ा हो सकेगा। वी आर वेरी थैंकफुल टू डॉक्टर सरमद अब्बासी, ख़ास तौर पे लाहौर से तशरीफ़ लाए हैं, दरस व तदरीस से वाबस्ता है, और ये कि मैथ कैट नामी इनिशिएटिव जो है इन्होंने लिया है, विच इज़ डेडिकेटेड टू मेकिंग वीडियोस दैट डिस्कस मैथमेटिक्स इन अ फन एंड ईजी टू अंडरस्टैंड वे। खुशी की बात यह है कि हर माह के पहले फ्राइडे को हमने दरख्वास्त की है सरमद साहब से कि वो हमारे लिए वक्त निकालें और हमें भी जो है मैथमेटिक्स समझने में, आसान अंदाज में समझने में मदद दें। और आई एम ग्रेटफुल टू हिम कि उन्होंने हमारी बात मान ली है। दोस्तों, मज़ीद वक्त ज़ाया किए बगैर जो है अब हम ये सेशन शुरू करते हैं। आप सबकी आमद का शुक्रिया।
Thank you, Nayyar. Thank you, so kind of you. So let's plunge in. So जैसे नैयर ने बताया, these are prime numbers, the first few prime numbers, and we study them in our elementary school. और ये वो numbers हैं, these are those numbers which cannot be written as a product of smaller numbers, right? And one is excluded, right? So a number that cannot be written as a product of smaller numbers is called prime, otherwise it's called composite. So for example, 6 you can write as 2 times 3, so it's composite. 5 you cannot write as a product of two smaller numbers. It can be only written as 1 times 5, but 5 is equal to 5. So, okay, so let me start this thing with something very simple. So how do you make a list of primes? Right? So suppose I give you a limit. I say calculate all the primes up to 100 or up to 1,000 or up to 1,000,000. Right? Then how do we do that? So there's a beautiful algorithm which is called the sieve of Eratosthenes. Okay? And so let me do that for you. Let me explain the algorithm for you. So what you do is you list down the numbers that you want. So in this case we could go to 67, right? So we're going to try to calculate all the primes up to 67. Now we know that 1 is not a prime, right? And now the algorithm says that go in this list and find the first number that is not crossed out, and that must be a prime, that's 2, right? But now all multiples of 2 are not prime. Okay, so you take hops of 2 and cross out all these numbers. Okay, so this way we get rid of all the even numbers. 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66. All right? And now you repeat the process. You search the list and you find the first number that's not crossed out, and that's 3. So 3 must be a prime. Okay? So 3 is a prime. And now all multiples of 3 are not prime, so you can cross them out. So 6 gets crossed out twice, but that's okay. All right? But 9 now gets crossed out. 12 gets crossed out twice. 15 gets crossed out. 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 60, 63, and 66. Right? And you repeat the process. And the nice thing is this gets easier as you go along. So the next prime we find is 5. And so now we take hops of 5. So we cross out 10, 15, 20, 25. This is the first time this got crossed out. Then 30, 35, we got another one. 40, 45, 50, 55, and 60, 65. All right? So we got these numbers. All right? And then now we repeat. Okay? And that's, so the next prime is 7. Right? Now we sieve with 7. So we cross out multiples of 7. So that's 14, 21, okay, 28. 28 plus 7 is 35, plus 7 is 42, plus 7 is 49. We got another one. Okay, plus 7 is 56, plus 7 is 63, and then we go over, so that's it. Okay, all right, and now, actually if we want, we could go on and do this with 11 and so on and so forth, but what you would observe is that 11 will not catch anything extra, because think about the multiples of 11. All right, there's 22, which was already caught by 2. There's 33, which was caught by 3. There's 44, which was caught by 4. There's 55, which was caught by 5. There's 66, which was caught by both 2 and 3. Okay, the first new number 11 will catch is actually 11 squared, okay, which is 121, which is out of our range. So I could do this, but I'll not get anything from it. So actually I could stop here. This is a slightly sophisticated reasoning. You know, if you want to do this with children, you don't have to do this. So the rest of the numbers here must be prime, which are not sieved out. Okay, 17, 19, 23, let's see, 29, 31, okay, we got one more than that, 37, 41, oh, 43, I missed, 43, 47, and we have 53, 59, 61, all right, so these, and 67. Okay, so these are the primes up to 67, right? And okay, so this algorithm, so I'm going to do things which are very simple, and sometimes I'm going to do things which are a little bit vague, you know, in the sense that I will not give you a proof, I'll just tell you the things, because getting to those things is a bit difficult. But let me tell you about the sieve of Eratosthenes. And one of the questions is, how much time does it take? Okay, and the answer is, well, first you write down all the numbers, so that up to n, let's say. So that will take time n, and then you start sieving with 2. So you take 2 hops, all right? So that will take time n over 2. You know, because you're hopping. And then it will take time n over 3, then it will take time n over 5, and so on. So this quantity is actually n over p, and you're summing with all over all the primes less than n. Okay, and you can, and there's an n plus here. So let me just calculate this, all right? And so you can pull out an n, and this is the sum of reciprocals of primes up to n. Okay, so this is a little bit like the harmonic sum, okay, except for it's sparser, far more sparser. Now we know that the harmonic sum up to n is about log n, all right? And number theorists can prove that this quantity is about log n, all right? Okay, so the total time taken is n plus n log n. All right. Okay, and this is actually so fast. Okay, so there is another quote by Karl Pomerantz that log n goes to infinity, but nobody has witnessed it yet. That this algorithm is so fast that, say if you want to, say you have computed primes up to 1 billion, all right, and you store them on a flash drive or something like that, and in your program now you want to read them back again. It will take you more time to read them rather than compute them again, because the sieve is so fast. And that's because reading from an external drive is far slower, 10 or 20 times slower. So you might as well recompute them using the sieve. Okay, it's really very efficient. Initially it goes slowly, but think about when you reach 23. You're just hopping along. Okay, so this is a wonderful algorithm, and one of the earliest great algorithms that was discovered by the Greeks. Okay, now let's ask a very simple question, which is, okay, how many primes are there? All right, and this is a question that we as children used to ask our teachers. They would say,
how sophisticated? How sophisticated is that proof, log n? Log n is something we encounter in physics quite often. Those are called Sudakov factors.
Yeah.
N means something else over there, but yeah, it's like that. What's involved in getting to log n?
No, it's not very difficult. It could be done in one lecture, but it's essentially playing with integrals and sums and doing approximations. Yeah, it's not very difficult, but it's technical. Yeah.
Okay, so it's like the sum over 1 over n that goes as log n, and that's approximated by an integral.
Yeah. So okay. So here's the first question that comes to mind. How many primes are there? And if you ask this question properly, we probably don't really know the answer if you make this question sophisticated enough. On the other hand, we do know the answer. Okay, and the answer was given by Euclid. Okay, and this is one of his most well-known proofs that the number of primes is infinite. Okay, and the proof goes like this. Proofs is by contradiction. Okay, and it goes like this. So suppose the number of primes is finite. Is finite. Okay, so then we could list them all. Okay, that's P1, that will be our first prime, P2, and up to Pk. That's what it means to be finite, that you can list those things, all of them. All right, and then he says, now consider this number n, which is made out of multiplying all these numbers, okay, and adding 1 to it. Right? So now this part is divisible by P1. Okay, so that plus 1 cannot be divisible by P1. Right? Okay, so if a number A is divisible by a prime, then A plus 1 cannot be divisible by a prime. And you can just think of a picture like this is, these are your numbers and here's 3. So you're hopping along, right? So if you've divided a number A, you can't divide the next one, right? And even if you're taking 2 hops, because the smallest prime is 2. So similarly, this number is divisible by P2, So this one is not divisible by P2, and so on and so forth. So you have created a number which is not divisible by any number in your list, right? So this number either itself is a prime, so you've discovered a new one, or it's divisible by some other prime which is not in this list. So there must be another prime. All right, so the list is not complete. All right, so this is mathematicians say that every person must learn this proof and keep it with themselves for the rest of their lives. It's like a little, something like a Shakespearean sonnet or some poem that you want to remember. Okay, so this is the earliest proof. Now, let me tell you it's very easy to prove that the number of composites is infinite. All right, here's a very, very simple proof. Consider 2n. Okay, all right. If you take n greater than or equal to 2, I've just given you infinitely many composites, right? Just for every n greater than 2, I've given you a composite number. So explicitly, I can give you infinitely many composite numbers. So that was Fermat's dream. His dream was to give an explicit formula, simple formula for primes. Okay, so something like, and what he did was, let me explain that to you. He defined what were called the Fermat numbers. Okay, and Fermat numbers are 2 to the 2 to the n plus 1. Okay, so doubly exponential, right? So let's compute the first few Fermat numbers. All right, so 2 to the 2 to the 0 plus 1, that turns out to be 3. We know that's a prime. 2 to the 2 to the 1 plus 1, that turns out to be 2 squared, so that's 5. 2 to the 2 to the 2 plus 1, that turns out to be 2 to the 4, 16 plus 1, 17. That's a prime. He's doing pretty well, right? It seems like he has found an explicit formula for primes. All right, and 2 to the 2 to the 3 plus 1, that's 2 to the 8 plus 1, that's 257. Okay, you can check in your prime list and it's a prime. And 2 to the 2 to the 4 plus 1 equals 2 to the 16 plus 1, and that's 65,537. That's a prime also. Okay, and that's how far he could go. And he conjectured that all these numbers are prime. Okay, that would be a beautiful proof. Look here, for every n I have given you a prime number. Okay, it turns out that 2 to the 2 to the 5 plus 1, okay, this number is a monster. This is 4294967,297. Okay, these things sort of grow in size very quickly because it's doubly exponential, so the number of digits doubles every time. Okay, and Euler in 1732 showed that this number was 641 times 6700417. Okay, all right, so this is not a prime number. So this is called F5, the fifth Fermat number. All right, and the sixth Fermat number is not prime. The seventh Fermat number is not prime. And every time anybody shows that a Fermat number is not prime, there's a lot of excitement in the number theory community. So nowadays people believe that only the first 5 Fermat numbers are prime. After that they're composite. They can't prove it. Okay, we don't know if there are infinitely many Fermat primes. We don't know if there are infinitely many Fermat composites. Okay, very, very simple question. All right, so somehow the Fermat's dream didn't come out to be true. Couldn't come up with an explicit formula for which generated only primes. All right, okay. All right, But nevertheless, and I'm not going to make this very technical, so we define f of n to be 2 to the 2 to the n plus 1, all right, okay. And for the mathematically minded, here's an exercise, all right. Show that f of n is actually obtained by taking the product of all previous Fermat numbers and adding 2 to it. Okay? All right? And for those of you who know induction, you should be able to do this. But here you see the kind of thing that Euclid was doing, multiplying all the primes and then adding 1 to it. All right? Exactly the same thing is happening, but here you're adding 2. And now what you do is you observe that all Fermat primes are odd. Okay? That means that this Fermat number cannot have a common factor with any one of these. Right? So each Fermat number is divisible by a distinct prime. And therefore there must be infinitely many primes. So you do get a proof, okay, that there are infinitely many primes, but you don't get your hands on the primes. They're buried in these Fermat numbers. Okay, all right? So that's one. And I want to do one more proof of infinitude of primes, and this is surprisingly recent, maybe 20 years back or 25 years back, and this proof is by Sidak. Okay? And I actually call it Sidak's conversation. Okay? And I'll give you some homework. So the conversation goes like this. So let's say this is me talking to a friend. Okay? So I say that A and A plus 1 have distinct prime factors. Right? That's right. So if my friend is mathematically minded, they'd say yes. Right? Okay. And then I would say that that means A times A plus 1 has one more prime factor than A. Right? Because I got all the prime factors of A and then I got all of them. So at least I got one more. And of course my friend will say yes. All right? And then I would say that hence there are many primes. Okay? And my friend would think for a little while and then they will smile. Okay? Start with any number A, let's say 1. All right? Then 1 times 1 plus 1 has at least one prime factor, that is 2. All right? Now start with 2. 2 times 2 plus 1, that has 2 prime factors. Right? Okay? And then 6 times 6 plus 1 has at least 3 prime factors. I can keep going, right? I can keep creating numbers with more and more prime factors. Start with any A, okay? Just use this formula, get one more prime factor, and keep doing this, right? So I prove the existence of infinitely many primes, okay? Once again, I don't get my hands on those primes, right? So that's.
So this proof is also by induction, huh?
Yeah, well, these three proofs, I classify them as divisibility arguments. Okay? Now, primes are the multiplicative atoms of numbers, right? But unlike chemistry, where molecules are harder to understand, in number theory, the atoms are harder to understand. Okay? There is another class of proofs which goes something like this, and if we have time, we may actually look at one of them, which says that if there aren't enough primes, then you can't account for all the numbers. All right? All right? In some sense, the variety in molecules forces a certain amount of variety in the atoms. Okay? So those are like counting arguments. Okay? There are hundreds of proofs of the infinitude of primes. You know, you could just go on and on. All right. Okay. All right. So now, next thing I'm going to do is I'm going to talk about some of the mysteries of primes, some of the things that you know we can't seem to figure out about primes. Some very, very simple questions. Okay, so and these questions are so simple.
Is there something that you can say about the density of primes? The 1 over a prime, the distance in some sense between
Yes.
them?
Okay. Yeah. So that we're coming to later. That's called the prime number theorem, which says how many primes are there up to x. All right. And it turns out they're x over log x primes. So density of primes up to x is around x is about 1 over log x. And you know, so this is where this quote comes in. Okay, you'd see how this thing comes in. Yeah. Okay. So some very simple questions about primes. So 3 and 5. Okay. These are primes which are only a gap 2 apart. All right. Other than 2 and 3, no primes can be consecutive. Okay, because one of them will become even, and so, you know, one of them will not be prime. But it can happen like 3 and 5, 5 and 7, 11, 13, okay, 17, 19. They can be a gap of 2 apart. So these things are called twin primes. Okay, twin primes. So if P and P plus 2 are both prime, we call them twins. Twins. Okay? All right. So here's a very simple question. Does the supply of twin primes continue forever? Or do we run out? Okay? Are there infinitely many twin primes? Okay? A very simple question that you can explain to a high school student. And the answer is we don't know. Okay? We still don't know. And there doesn't seem to be a very big hope of solving this problem in the near future. But you know, you can never tell. There are geniuses out there, right? I can tell you that there was a big breakthrough on the twin prime conjecture, which was, so what you can do is you can think of these numbers, you know, lying on a line, right? And then you color them orange if they happen to be primes, right? And think of a train of size 3, okay, which is running through here. And every time 2 primes fall in it, it rings a bell. All right? So the question is, will this train continue to ring a bell forever? You know, will the bell ring forever? That's the twin prime conjecture. So there was a mathematician, I think I've written his name. Oh yeah. And this is the last decade. Yeah, Tang. Okay. who was a mathematician, and he was actually making sandwiches at that time. He didn't have a proper job. Okay, and what he showed was, don't take a train of size 3, that's too restrictive, but if you take a train of size 7 times 10 to the 7, okay, 2 primes fall on it, the bell will ring, and that bell will ring infinitely often. Okay? All right, so his train is huge, but it's a finite train, and 2 primes will keep on falling inside it, and the bell will keep on ringing forever. And this was a huge breakthrough in the twin prime conjecture. Then there is a project called polymath. Okay, and polymath is a interplay. A polymath is somebody who knows everything. Okay, and poly also can be many mathematicians. So they collaborate on the internet, okay, and work together. And they were able to reduce this to 246. Okay, their train size was 246. Okay, so fairly reasonable, but still far from train size of 3, which the twin prime conjecture says. And but there is, so it's a good news. There's a huge progress on this problem, but these people have also figured out that their methods will never reach the twin prime conjecture. Somehow they figured out that they will get stuck at 30s or something like that. The train size, they'll never be able to argue it down to 3. Okay. All right, so that was one. Another problem about, I keep I keep permuting my notes. Yeah. Okay, here's something called Bertrand's postulate, okay? And I have no idea why it is called a postulate. Probably it is a conjecture, okay? It is not a postulate because it says that there's always a prime between a number n and 2n, okay? Right? So if you take a number and it's double, you'll always find a prime in there, right? So this theorem was proved by Chebyshev, all right? And he used some very heavy mathematics to prove this Bertrand's postulate. But it was then later on proved by Paul Erdős, okay, in a very famous paper when he was very young. And his proof was like very beautiful and used very simple mathematics. And they said that after Paul did that, he said, Chebyshev said it and I say again, there's always a prime between n and 2n. Okay, all right. But so Bertrand's postulate is now a theorem, but here's Legendre's conjecture. Okay, which says that there's always a prime between n squared and n plus 1 squared. Okay, so there's between two squares, consecutive square, you will always find a prime. So think about it, 16 and 25, okay, there are lots of primes there. 25 and 36, there are lots of primes there. And the thing is, if you experimentally try this, it gets easier and easier. There are more and more primes, between these gaps as you go further. But somehow, embarrassingly, we can't prove this. Okay?
Even these statements. Even these statements tell you that there are infinite many primes. So
Yeah, any of these will imply that there are infinitely many primes. Yeah, yeah. Okay. All right. So here's another one, which is called Goldbach's conjecture. Okay, and it says that every even number greater than 2 can be written as a sum of 2 primes. Okay, so 4 you can write as 2 plus 2. 6 you can write as 3 plus 3. 8 you can write as 5 plus 3. 10 you can write as 3 plus 7. Okay, 12 you can write as 5 plus 7, and so on. Okay, and once again, as you go further away, there are more and more ways of doing it. It gets easier and easier if you're really looking for it. Once again, there's no proof of this. There's people have been working on it for 400 years, 300 years, and people haven't been able to solve this. Now, okay.
perhaps the simplest unsolved.
This one? Yeah, or the twin prime conjecture. Both are equally simple, I think, to state. Yeah. Okay, there was something I had about. Yeah, okay. All right. Okay, so a little bit of sort of fun stuff to tell you. Okay? Yeah. All right, so let me tell you a little bit about what are called Mersenne primes. Okay, so Mersenne primes are of the form, so MP is actually 2 to the power P minus 1. Okay, so you raise 2, and this P has to be a prime, okay, because you can show that 2 to the power AB is equal to 2 to the power A minus 1 times 1 plus 2 to the power A plus all the way up to 2 to the power B minus 1 A. Okay, you guys can check this at home, right? Yeah. Okay, so this tells you that if you, a minus 1 here, that if you take a composite here, you will get a composite. So if you want to get a prime, you must have a prime here. All right, so these are called Mersenne primes, and because of their special properties, what happens is if you take a prime here, sometimes you get a prime, sometimes you get a composite. Okay, but if you take a composite here, you always get a composite. So what you can do is you can take a prime here and try to check if this number is prime, and because of its special form, it's easy to test for primality for Mersenne primes. So the largest known prime is a Mersenne prime, and let me tell you what it is. Okay, it is 2 to the power 825,899,33 minus 1. Okay, and it has 24,862,048 digits. Okay. All right, and now people say we know it's a prime. I don't know what it means to know. The definition of knowledge actually gets. By the way, it's very easy to memorize this number in binary. Okay, because it's just 1, 1, 1, 1, 1. You keep saying that these many times, minus 1. Okay, in binary it's just it's a very so if I were to say this number in binary and I were to say 1 10 times in a second, you'll have to stay here for a month before this number ends. Okay, so so there are these computational nice things about primes. Okay, so now let me get a little bit serious. Okay, and I'm going to talk about a little serious stuff. Okay, and that was what Parvez was asking. Is one of the greatest achievements of mathematics is what is called the prime number theorem. All right, and the question is how many primes are there, right? That was the simple question. Primes are there up to, and now we make the question a bit more sophisticated, up to x. All right, and the prime number theorem says, and this number is defined as pi of x. This is the number of primes up to x, right? And the beautiful prime number theorem says that pi of x is asymptotic to x over log x. Okay, right? And what this asymptotic means is the ratio of two functions goes to 1 as x goes to infinity. All right, and there is another few things that I want to say about this is currently so there is you people may have heard of the Riemann hypothesis, okay, which is about the zeta, something called the zeta function, right? Riemann zeta function. So in number theory, usually you have results which either use the Riemann hypothesis or not. Okay, Riemann hypothesis is such a powerful thing that many theorems in number theory are, if the Riemann hypothesis is true, then this conclusion, so on and so forth. Then we understand so much about primes. Now, if you prove the Riemann hypothesis, you prove all those theorems, right? So there are number theorists who exclusively assume the Riemann hypothesis and prove new things from it. All right? And there are number theorists who say, well, it's an unproven thing, so we're not going to use it and we are going to try to get the best results we can. And then there are those who work on the Riemann hypothesis, so there are these kind of. Now, if you don't assume the Riemann hypothesis, then pi of x is x over log x, okay, plus there is an error term. All right, and this error term means plus or minus, right? And so this error term is something like x times e to the minus a square root of log x, right? So that's how the error term is like.
What's a over here?
A is a constant. A is explicitly computable constant. Yeah, okay. And if you assume the Riemann hypothesis, then the error term is actually square root of x log x. Okay? All right. Now, if you're a statistician, you sort of realize as if God was throwing away prime numbers, and this is the standard deviation. You know, the standard deviation is typically the root of the quantity that you're supposed to get. All right? So, in some sense, if the Riemann hypothesis is true, then prime numbers are really spread like random numbers. Okay? And not only the average is right, but the standard deviation is also what you would expect it to be. Okay, so one more.
So, normal distribution. Are you suggesting it's a normal distribution?
No. Here you're only computing the standard deviation. I will tell you about the normal distribution in a little while. So this is just the standard deviation, right? You know, if you have a quantity which is averages x, then you know the standard deviation is about root x, right? So that's what the Riemann hypothesis will imply. Okay, that you have the standard deviation right, but you don't know about the third or fourth moment. You know, okay. All right. So here is the quote that is by Paul Erdős, right here. Let me correct that. That quote is not by Paul Erdős. Okay. That quote is by a mathematician called Karl Pomerance. Okay, and what happened is, I think when Erdős died, he was there was some conference in his honor, and you know, Karl Pomerance came there, and there he said that about there was something called the Erdős. I don't know how to pronounce this. I tried it on Google. It was saying Kach, right?
There's
Polish.
also a Kach-Moody algebra.
Okay, yeah. Erdős-Kach theorem. And Karl Pomerance, you know, when he was talking about this theorem, he said that, you know, if Einstein met Paul Erdős and Kach, Einstein would say, well, God doesn't play dice with the universe. And they would say that may be so, but surely there's something strange going on with the primes. Okay? And this got misattributed to Paul Erdős. All right? So if you do Google search, you know, the quote is always being attributed to Paul Erdős, but he actually never said it. But let me try to explain to you what this theorem says and see how shocking it is. Okay, now remember when we did the sieve of Eratosthenes? We were crossing it out, right? And we said that things will cross out. The total time would be n log n, right? So that means on the average, something will be crossed out log n times, okay? Which means on the average, the number of distinct prime factors a number will have would be something like log n. All right? Okay? All right? So so if you have a number n, right? Omega of n is the number of distinct prime factors, okay, in n, right? So what Erdős-Koch do is they count the number of distinct prime factors, they subtract what they expect from it, okay, and they divide it by the standard deviation of this. All right? Okay, and now what you do is you look at all n which are less than x, right? Such that this quantity is all right. So you're looking at things which are within a certain number of standard deviations away. This is the typical thing that you do in statistics. All right, and this turns out to be okay. I think there's a normalization factor, which is probably 1 over 2 square root of 2 pi, right? Okay. Yeah. So what you do is you look at what falls within A and B standard deviations away, right? And if they were normally distributed, you would get this answer. And this is saying in the limit you get that answer. Right? So as if the number of distinct prime factors is just randomly thrown between integers. Right? And that's why that quote by what's his name? Karl Pomerantz.
So if I take b go to infinity, then this becomes the error function a.
Yeah.
Okay. And if I take a, I can't take a equal to 0, can I? 0.
Well,
Can I take a equal to 0, then b is, and b equal to infinity, in which case this will give me 1.
No, it'll give you half.
Half.
So yeah, half the time you would be, you will be erroring in the positive, half the time you'll be erroring in the negative. Right? This is just exactly what you, this is the normal the error function for the normal distribution. Actually, this is the, so, here's the, here's the normal distribution. This is A, this is B, and this is counting this area. Right? Typically, we count the area which, what is the probability that we fall outside. All right? Okay. Okay. All right. So now let me talk a little bit about applications, because people are always, for some reason, interested in applications. Okay. And, okay. Here's a problem for you to do in like 3-4 minutes, all right, which is factor 9991. Anybody wants to give it a go?
We'll let you do it.
Okay, so the trick here is to realize this is 10,000 minus 9, okay, which is a difference of 2 squares. That's 100 squares minus 3 squared, and that's, 100 minus 3, 100 plus 3, so that's 97 times 103, okay. So that trick in this case works. Now let's look at the asymmetry between multiplying and factoring, okay, very superficially, right? So if you have a number n which is d digits, okay, you could, all right, then the number n itself is something like 10 to the d, right? It has d digits. So the number n is actually huge. It's exponential. I mean, if you're doing it in binary, it will be 2 to the d, but it's exponential in the size. Now, when you multiply two d-digit numbers, the elementary school algorithm takes d squared time, right? We did that last time, and you can, so the time, and this is the simplest algorithm, you have better ones, but the time is proportional in the polynomial in the number of digits. All right? Think about if you want to factor a number n and you start trial dividing it. So you divide it by 2, then 5, 3, 5. You can divide it by odd numbers or something like that. You can try to be a little clever. You will have to go all the way up to square root of n, right? Till you are sure that, it's not going to be factored, right? And this is something like 10 to the power d over 2. Okay? All right? And this time is exponential in d. It's huge. Okay? So if you have a 100-digit number, multiplication will require time something like 100 square, which is 10,000 operations. Okay, maybe a constant times that. But if you have a 100-digit number, trial division may require 10 to the 50 trial divisions. It's never going to end, you know. The universe is going to end, but you won't be able to do this calculation. So there's this asymmetry between multiplication and factoring. All right? And this asymmetry can be used by cryptographers to do encryption. All right? And so there is this very famous method called RSA, named after three mathematicians, Revest, Shamir, and Alderman, okay, which uses this asymmetry between multiplication and factoring to do cryptography. You can send messages, you can encode them, all right, and what the thing is that there are two keys, all right. One key is called a public key, the other key is called a private key. So what I do is I take two large prime numbers, I multiply them, and that I make it public, and that is known to everyone. But to encode those messages, decode those messages, they need to know the two factors, all right. But that's exponentially hard to find out. Okay, all right. So cryptography is one place where, you know, the prime numbers and number theory is used, and this was a very surprising application of number theory. Before that, people thought, you know, there aren't many applications. There's another very beautiful application, which is, how do you generate a random number using a computer? All right, and physicists would love to generate random numbers. They do all kind of simulations, you know, Monte Carlo simulations and all that. So you need to be able to generate random numbers. And it turns out that, you know, this Erdős-Kac theorem and the prime number theorem and other evidences show that prime numbers seem to be random. You know, they appear random, right? So we can use that to generate random numbers. Typically, what people do is they start with something called a seed, okay, which is S, all right, and they generate the next number. So let's call this S0 by multiplying the seed with some A, okay, adding some constant b to it, and then taking the remainder, okay, where p is a large prime. Okay, so this is called a linear congruential random number generator. It's not really a random number generator, it's called a pseudo-random number generator, in the sense that the numbers that come out of it pass all kinds of statistical tests. Okay, so random number, actually, you know, there's a quote by John von Neumann that the generation of random numbers is too important to be left to chance. Okay, so you know, there is a whole theory behind it.
So what this means is that if you boot your computer and you put in this and let it generate a random number, each time it will give you the same random number.
Yeah, if you give it the same seed.
If you give it the same seed,
absolutely.
So it's pseudo-random.
Yeah,
in
that's
that
why
sense.
we call it a pseudo-random. Yeah, yeah.
Why not use a physical process then?
Well,
which is truly random.
Oh, yeah. So there is a whole theory in computer science. What it is it's about taking truly random bits, okay, all right, and then, so this could be a physical process, but the thing is that when you do this, you may be able to get 20 bits or 30 bits, right? From there, can you stretch this, okay, into a very long sequence which is indistinguishable from a random sequence. Okay? All right? And so there's a whole theory behind it. So the seed is the true random thing. All right? And this is just making it.
And This is for a flat distribution.
A uniform distribution.
Uniform.
Uniform distribution. Then there's a whole theory. Once you have uniform distribution, how to get normal distribution and all other kinds of distribution.
But what if one can change A and B as well? Then
Oh, by the way, yeah, the choice of A and B is supposed to be done very carefully, number theorist. Otherwise, you can get very short cycles if you've not chosen them properly.
Mm-hmm.
Yeah, it's a whole, like hundreds of papers have been written on it because it's so important. Yeah. So typically, what they do is they take the seed is random. So if they want it to be truly random, what they do is sometimes they read the clock, or they read, something like that to make it really random. But there's a lot of merit in being able to generate the same random numbers over and over again, because that allows me to cross-check sometimes programs, right? So, okay, and maybe I'm going to say one more thing. Okay, so, all right, okay, one more thing. I wanted to talk about quantum algorithms, and you people must have heard of this, Peter Shor's quantum algorithm. And so that is an algorithm. If we can implement quantum computers, then factoring would be, we can do it in polynomial time in the number of digits using a quantum computer. It's not probably d squared, it's probably d to the power 4, but nevertheless it's not exponential. All right, and then I think that is one of the big triumphs of quantum computing, right? Shor's algorithm is a cornerstone. It's a very interesting algorithm. But it's pretty difficult. It requires a lot of background. So, but the challenge that factoring brings, brought out this wonderful piece of mathematics for us. So, but people can talk about prime numbers for hours and hours and hours. So, I think I've sort of ran out of steam, and so let's stop here.
Thank you so much. It was really nice to recall all these things that we have learned in number theory, essentially. What I was expecting when you were talking about the prime number gaps is James Maynard. You should have mentioned him, because he brought down the gap to 6, right? And he won the
Maynard.
James Maynard, yes.
Maynard, yeah.
2022 Fields Medal for
Medal,
his work in
yeah.
analytic number theory, and
Yeah.
recently has been selected as the fellow of the Royal Society. So I think you should give some credit to him.
Yeah.
as well.
Well, definitely Maynard, Terence Tao. These guys are amazing. So I didn't know that Maynard had brought it down to 6.
Yes.
Okay, so he's brought down the train size to 6.
Yes, with the polymaths.
But then why wasn't that on Google? On Wiki?
It must be there. I haven't checked.
So do double check. If I know Maynard and Tao did it independently.
Yes, the polymath group brought it down to 6, I think, and
Okay.
and he brought it down to 4, I guess, as far as I remember. But yes, we can double check it.
We can double check it. Yeah.
But still, 2 is a challenge. So have you given it a try yet?
No.
Okay.
I was curious about these Fermat's numbers because they do not capture all the prime numbers.
No.
So what is the significance then? Why are they important?
Oh yes. Okay. Yeah. So one of the things is actually I've written this thing down. So let me. There were so many things that I could have talked about. Yeah. So okay. One thing is that can we write a formula which only generates primes? Okay. that's a weaker challenge than can we write a formula that generates all the primes. You know, what you would want is a formula for the nth prime, you know. Okay, that would be like ideal, right? But that's a very tough goal. So people are saying, can you give us a simple formula in which we only get primes? We don't get any composites. That's an easier task. So Fermat was just trying to do that. So let me tell you something about, people talk about formulas of primes, okay? And if I can find my formula, I mean the formula that I had written, yeah, I've found it. Okay, so is there a formula for primes, right? And the answer is, what is a formula? You must ask this question, you know. So for example, what are the functions that I'm allowed, what are the elementary functions that I'm allowed to use there? Am I allowed to use trigonometric functions? Am I allowed to use elliptic functions? Am I allowed to use, okay? So one has to define what is a formula, all right? And people think that there are no formulas for primes, but let me write one for you, okay? And and this formula says that the nth prime is actually equal to 1 plus sum going I from 1 to 2 to the n, okay? And okay. Let me write the pi over here. Okay, all right. So this is a formula that will tell you the nth prime. You put a n in here and you compute this and you'll get the nth prime. It's a mess, okay?
Is that the floor function?
Yeah, this is the floor function. There is a floor function here, okay? And if anybody wants, I can explain this to them. At least I can explain you this part. The rest is easy. But the thing is, to compute, in some sense, this is making you compute all the primes. In fact, make you do more work. Okay, because think about it, you're going to go from 1 to 2n, and then you're going to calculate these factorials, all right? And then you're going to divide, and then you're going to multiply, then you're going to calculate cosines, and then you're going to take the floors, all right? So it's a very complicated formula, all right? And Herbert Wilf says that this cure is worse than the disease. Okay, all right.
You get the first one.
Huh?
N equal to.
Okay, so let me just show you this part. Can I just talk a little bit about this part if you want? Okay, so this one is saying j is going from 1 to I, floor of cosine of pi times j minus 1 factorial plus 1 over j, all right? Let's just look at this thing. Now there is a Wilson's theorem which says that j minus 1 factorial plus 1 is divisible by j if and only if j is either 1 or a prime. Okay? So when j is 1 or a prime, this becomes a multiple of pi. And cosine of a multiple of pi is either minus 1 or 1. So for every prime, okay, this number is, square of this number is minus 1 or a 1. For every composite is something else, you know, strictly less. So when you square it and take the floor, this number is only going to be 1 when j happens to be a prime. Okay, so you know, but you're doing everything there, you know. So this is.
It's always a 1 and you're dividing n by 1 and then getting.
Yeah. Yeah, so if you put an n here, okay, this actually gives you pi of n, the number of primes up to n. For every j which is a prime, it will give you a 1. For every composite, it will keep giving you 0. So this is, let's forget that's even more complicated, right? But it's a meaningless calculation. Nobody would, doing this calculation is harder than actually working out all the primes
But
up
that
to there.
base is true. I mean, it gives all.
Yeah, it's true. Yeah. So, yeah. It just proves a point, and it forces you to think what a formula is. So for example, people say fifth degree polynomials, there is no formula for that. Well, there's no formula in terms of radicals. But if you allow elliptic functions, there is. So, okay. Shall we end here? Okay.
Yes.
Okay, thank you. Thank you.